Hello, I'll present our paper titled On Orbital Stabilization as an Alternative to Reference Tracking Control. The aim of the paper is to demonstrate, using simple examples, that orbital stabilization often can be a suitable alternative for feedback design of certain types of motion control tasks. The main contribution of the paper is to the use of so-called excessive transverse coordinates, as well as the linearization of their dynamics, so-called transverse linearization, for the design and analysis of orbitally stabilizing feedback. We will consider the example of a double integrator system, in which Q can be thought of as a position variable, and with a single control input U. The task will be to generate oscillations of the form as shown here, with some given amplitude A and frequency omega, but in which the phase phi is taken to be arbitrary, in the sense that the timing of these oscillations is not important. Now, this could, of course, be solved using some sort of reference tracking controller. For example, if we defined the tracking area as follows, which note that we have taken the phase phi to be 0 as it is arbitrary, then the controller, consisting of a feed-forward term, which is just the twice the time derivative of the reference signal, and a PD feedback, will result in asymptotically stable aerodynamics if the gains Kp and Kd are taken to be positive. But if we start with the initial conditions as shown here, which are actually part of the desired orbit defined by the reference, then the initial velocity error will be non-zero. Now, this means that if the timing of the motion is unimportant, then this might not be the best choice, as we actually, even though we start on these desired oscillations, we will have non-zero errors. Of course, we could just choose the phase of which is arbitrary, depending on these initial conditions, but this would then require an extra layer in the control law. Now, as an alternative to reference tracking for the considered task, actually to stabilize periodic trajectories of time-invariant systems in general, is to restate it as an orbital stabilization problem. That is, suppose you are given some desired periodic trajectory Q star of some minimal period capital T, and define the corresponding periodic or closed orbit eta star as all the states of the system along this periodic solution. Now, the task of orbital stabilization is then to design a time-invariant controller, so a strictly state-dependent controller, such that the desired orbit eta star is asymptotically stable, or equivalently that the desired solution, Q star, is asymptotically orbitally or Poincaré stable. Now, this is just the same as eta star being stable, and the distance to this orbit, that is to eta star, going to 0 as time goes to infinity. Now, in order to design orbitally stabilizing feedback for the considered example, we will propose two methods, both of which are based on so-called transverse coordinates. So the first method is based on a single transverse coordinate and follows from the following proposition. Let W be a known, unique, bounded, and non-vanishing solution to the following initial value problem, given some second-order system as shown here. Then any state which is on the desired orbit, which is defined by the solution W, then this scalar function I, defined as follows, vanishes. So this function I is what's called a transverse coordinate. So it vanishes when the states are on the desired orbit, but it is non-zero away from it, such that if we stabilize its origin, we will also stabilize the periodic orbit as well. Now, in order to stabilize the origin of I, we propose the following controller. Let U sub I be taken as follows, with Ki some positive gain and the sign plus function defined as shown here. Then the solution W of the initial value problem is rendered and locally asymptotically orbitally stable solution of the double integrator system. Now, for the considered example, the initial value problem can then be set as follows. It is well known that this problem with omega squared and given the amplitude as the initial condition has a solution as we desire. Function I becomes defined as shown here, and the feedback or the control law is given as follows. So this will indeed stabilize the periodic orbit, but only quite locally. Moreover, it can be a bit hard to generalize to systems with higher degrees of freedom. Thus, we introduce a more general approach using an excessive number of transverse coordinates next. In this regard, we will introduce a reparametrization of the normal orbit. That is, we define the function phi(s) as a sine s, phi prime as its derivative, and theta s as the frequency omega. Here s can simply be thought of as a rescaling of time along the normal orbit, meaning just that its nominal velocity along it should equal to the frequency omega. Now this means that these functions can be used to define this reparametrization, meaning that the following set of relations must hold along the normal orbit. S must just satisfy the following relation for a given trajectory, an example of which is to take it as shown here. We define this as some mapping P, and P is what we call a so-called projection operator, meaning that if we know the states of the system in a neighborhood of the normal orbit, then we can project down upon the orbit in order to recover this variable S. Now this we can use to define a set of transverse coordinates for this orbit. These are shown here, in which we may note the difference between y dot and z in the sense that y dot requires the actual velocity of the parameterizing variable s, whereas in z we use just this nominal velocity, in this case omega, found through the function theta. So the question is then, which should we pick in order to design a controller? Well, for one, we have already chosen one variable, namely s, in order to find the position upon the orbit. Now, that means that there's one variable left to choose in order to then form a well-defined diffeomorphism, so a change of coordinates. The only one which is independent together with s at all time moments along trajectory, in this case, is psi, but it depends on s dot, same as y dot, which also depends on s dot. And both of these then will require knowledge of q double dot, as p is dependent on q dot. Now, this is not ideal. Thus, we suggest choosing y and z, which then only depend on the states of the system, namely q and q dot. And we will show that you can use these two coordinates, which form an excessive set of transverse coordinates, in order to stabilize the trajectory in orbital sets. Now that brings us to the following proposition. Suppose that for some positive gain kz and for any gain ky, the control law is taken as shown here, in which y, z, and s are defined as on the previous slide. Then the desired trajectory q star is rendered exponentially orbitally stable. So notice here that this control law is very similar to the reference tracking control law we have defined earlier. So it consists of something similar to a feed-forward term of the reference and to a PD feedback. However, compared to the reference tracking controller, which is time-dependent, this is completely time-invariant in the sense that we only need to know the states q and q dot in order to compute it. It also differs in the fact that whereas the gain in the PD controller, the KP gain, has to be positive, it's only the KZ gain which needs to be positive for this orbitally stabilizing feedback. Although taking ky greater than 0 is likely advantageous in terms of the convergence rate. In some sense, it is actually the steps taken in the proof of this statement which is the main contribution of this paper. But due to the time constraints of the talk, we will only outline the main points of this proof. So for this, we define the following vector of transverse coordinates consisting of y, z. The projection operator is taken as on the previous slide, and we define x sub s as the normal trajectory parameterized in terms of this variable s. We then take the simplest form of the control input, so it consists of the normal control input parameterized in terms of s, which can be found through the following expression, and some feedback term consisting of a constant matrix K, which is just the gains Ky and Kz. You can have more complicated expressions as well, but we keep to the simplest to keep things simple. Based on this, we derive the linearization of the dynamics of these transverse coordinates so-called transverse linearization for this system. This results in a 2-pi periodic linear system with some transversality constraints. So it's a differential algebraic equation. Here, dp is just the Jacobian of the projection operator evaluated along this normal trajectory. Now this just means that locally these transverse coordinates are orthogonal to the gradient of this projection operator, and hence they are also transversal to the normal flow of the trajectory. The third step is then to derive a condition for the stability of this system. Of this, we show that it is equivalent to the integral of the trace of this periodic matrix, evaluating or becoming negative over the period. Now, for those familiar with the Poincaré test for checking the stability of periodic trajectories of planar systems, it is more or less equivalent to that. Then lastly, we show that for the considered trajectory, this condition just corresponds to the gain kz being positive. Now we have so far in this talk introduced 3 different control strategies for achieving these oscillations of the double integrator system. And now we'll compare them in numerical simulations to highlight the differences. So I was hoping to show you experimental data from a real system, which we have implemented successfully. But due to Corona, we'll have to make do with numerical simulations this time. But it's quite easy to implement these yourself, so feel free to give it a go if you want to. So we have the reference tracking PD controller, which is given in, by the blue solid line in the plot to the right. The single transverse coordinate controller given in black. The one using excessive coordinates given in red. We simulated this or compared them on the following system in which the mass is 50% above the normal value, as well as there is some which is subject to a dry friction term. So I don't want you to pay too much attention here to the convergence rates or where these controllers settles, as this is more or less just a tuning issue, so you can change the controller gains somewhat and get better performance. What I wanted to illustrate and highlight here is the difference between these 2 strategies. So whereas the orbital stabilization trajectories quite gradually and smoothly settles into periodic orbits quite close to the normal orbit, which is given by the green dotted line, the reference tracking controller is quite aggressive, so it goes fast towards the normal orbit, leading to a quite large initial force. But then the reference signal has moved on, and in a sense it has to backtrack somewhat before eventually settling into a periodic orbit. So this therefore highlights that if you have some motion control task in which the timing is not too important, but it is important just to get close to the desired behaviors of periodic orbit, then these orbital stabilization strategies can be indeed be quite well suited alternatives to the simple reference tracking controllers. In the paper, we also show that these types of methods also can be used to achieve orbital stabilization of certain types of non-periodic motions. And specifically, we give the example of a start-stop motion and showed how you can then design an orbital stabilization controller, shown here, and compare it to a reference tracking controller of the following form. Now, due to time constraints, I won't go into more detail in this talk, but please feel free to look at the paper for more details on this example. So these methods can therefore be used to a certain extent for non-periodic trajectories. But what about higher dimensional systems, non-linearities, underactuation, uncertainty? For example, what about control-affine systems with non-linearities of this form? So we are working on generalizing this approach to these types of systems, and in which the general idea is, for instance, this start-stop type motions. You have a parameterization, you have a projection operator to recover the parameterizing variable. Then you can design a feedback of, for example, this form with some varying feedback matrix K, in which you use an excessive set of transverse coordinates. Now, this approach can then be seen to some extent as generalizing the ideas of Hauser and Hinman for feedback linearizable systems. And we hope to publish this soon. We also hope to come with some further results on how you can actually handle uncertainties for these types of systems as well. That was what I had time for. Thank you.